if the best angle, if A can throw to C, and that's the maximum range, right? If they throw it to B with the same velocity, is there more than one trajectory to B? And then the other question is, what is that best angle? What do you think? Do you have an idea? What's the best angle for throwing something?
45 degrees is exactly equal to vertical.
Bobby thinks it's 45 degrees because it's exactly equal horizontal and vertical. Do you think 45 is the best? How many think 45 is the best angle for range? Bobby does, I do. Anybody else?
Well, you do.
Oh, wait. Bobby does. Oh, yeah, there we go, right? Okay, so we got a few votes for that, yes? Yeah? Okay, now, how about, what if we use the same velocity, but we change our angle so that the velocity, so that it doesn't go as far? So we throw at the same speed, but we just change our angle so it doesn't go as far. Is there more than one trajectory that will reach B?
Yes.
Yeah, what is it? What are they?
One really high, one really low.
Yeah, one really low, one really high, right? So, low and high, same velocity maybe, right? Yeah? And you see these in football, don't you? When do you see the low trajectory? Yeah, short passes. Who's going to catch? There you go. That's okay. Okay. He's got it. Here. These are, I can catch these. Okay. Yeah, so the passes are short and fast. The only difference is the high trajectory, of course, takes longer to get there. Okay. If you recall, the time in the air on these types of problems is determined solely by the vertical, right? It's like this, right? It's a problem like this. The faster I throw it up in the air, the longer it stays in the air, right? So it's the vertical component that totally dictates how long it's in the air. The horizontal dictates how long it takes to get there. Does that make sense? Okay, so that's what we're going to do. We're going to derive the equation here, the range equation. Okay? And you guys have all your trig identities memorized, don't you? Yeah, good. Because we're going to need one trig identity out of all those hundreds that you memorize. Okay. We are launching, be very, very quiet. We are launching at a velocity of v at an angle of theta. That gives us a horizontal component of v cos theta. Yeah? Where am I? I'm on the screen. Okay, that's good. And we've got a vertical component of v sine theta. Yeah? Now, our range is going to be, and it always works out this way, right? Isn't it always horizontal component times time in the air? Yes, it is, right? So it's going to be v cos theta times time in the air, right? Now, if you recall on these types of problems, the time in the air is just, well, isn't it just twice the vertical velocity divided by 9.8? Isn't it? It really is, because it's the vertical velocity divided by 9.8 to get to the top, and then it's that again to get to the ground, right? So this becomes, well, v cos theta, and then the time is just twice v sine theta over g, where g is 9.8. You've done enough of these, I think, already, that you recognize that. Only now it's a formula, right? And there it is, we have a formula. Are you excited? Oh yeah. Are you excited enough, though? I don't think you're excited enough. Now, let's clean things up a little bit, right? So v times v is v squared over g, and then 2 sine theta cos theta. And that's easier than solving the Suvat problem, isn't it? But it's not easy enough. And it also has a problem, okay? And by range, I mean the horizontal distance that it travels, right? This is our range, right? It has a problem. How do we solve for theta? Because tomorrow, can we not do that? Thanks. Put that away, just, yeah. Okay. Tomorrow, I'm going to tell you how far away the target is, and you have to calculate the angle to hit the target. Yes? How are you going to do that with this? How do you solve that for theta? Well, you can't, remember the trick is that you get the trig function by itself, right? And then you do the inverse of the trig function. But there is no inverse sine cosine, right? Isn't that right? So what we have to do is substitute for 2 sine theta cos theta. We have to substitute something. And what is it? Do you remember? Here's where it's IQ on the line. Yeah, but that would get rid of sine, but not cosine, right?
Inverse of sine squared. Tangent.
Tangent sine over cosine. What is it? Does it look familiar? 2 sine theta cos theta. It's not 1 either. What is it? Sometimes somebody will come up with it. Sometimes kids like open up their binder and they find all the trig identities. Or sometimes I just say that it's the sine of twice the angle. Do you remember the double angle theorem? No, but it is, right? Okay, so 2 sine theta cos theta is just sine of twice the angle. Okay, so our formula for the range is this. Range equals v squared over g sine of twice the angle. Yeah? Now, let's check one of our guesses. One of our guesses was that 45 degrees was the best angle. Yes?
Yes.
So what is twice 45?
90.
90. Sine of 90 is?
1.
1. The biggest sine we'll ever get, correct?
Yes.
Therefore, the greatest range that this formula will ever predict, correct? Yes, there we go. So it looks like we're on the right track, right? Here's another interesting thing. If we put in, remember sine is the y coordinate on the unit circle. Okay? If I put in, let's put in 20. Well, twice 20 is 40. 40 is like here. What if I put in 70? Twice 70 is 140. Isn't that right here? Isn't there some symmetry there? Yeah, this one's 40 degrees above this thing, and this one's 40 degrees above 180, isn't it? 140 being that. Don't they have the same y coordinate? Yes? Yeah, and they're going to predict the same range. Isn't that interesting? So if 20 hits the target,
So it's 70.
70 is going to hit the target. If 30 hits the target, 60 will hit the target. If 10 hits the target, 80 hits the target, right? So remember those 2 trajectories, right? The low trajectory and the high trajectory, they're complementary. The 2 trajectory, the launch angles are complementary. Isn't that wild? It's a little bit wild. Yeah. Okay? Yeah. Okay, so let me invite you back in time. Can we not talk? Thanks. Okay, let me invite you back in time. We're going to go back in time to 1990. In 1990, this school wasn't built yet. Yet there existed a company called Vernier Software. It wrote some code for us that still works. Right. Yeah. And the system requirements are pretty stringent here. You have to have 80 kilobytes of RAM and at least 16 colors.
Darn it.
Yeah. This isn't the real high-res stuff. It's 256 colors, right? We're not going to tax your system at that point. But 16 colors, there it is, right? Okay. Don't even dream of using your mouse. You cannot. There's no mouse cursor. But the arrow keys work. Okay. So here's the ground. You're going to do, for the lab, you're going to do a cliff. You're going to do the ground, and you're going to do a moving target. Okay. Now, after we got this, we actually got this simulation software called Interactive Physics. And that stuff actually lasted from 1995 somehow, or 94. We had it in 94, I know for sure. It lasted from then until last spring. And then somehow they updated Windows XP and it no longer works. And I've tried to make it work and I just can't get it to work, right? So we're back to like the original stuff that we did when the school opened. That's okay. But when we get I'm trying to get money for the new software and it's going to be very good. But let's go back up here and let's look at the ground, okay? And then somebody give me a velocity that your air rockets shoot at.
200.
36. Okay. So you guys shoot at 36. So let's plug this into our calculator. When you plug this into your calculator, you're going to go 36 squared divided by 9.81 times sine of twice. And then let's launch it at 20 degrees. So let's go twice 20. Okay. So try that and predict where it's going to go.